This is the 11th video in this series dedicated to Bessey shuffle diagrams. As a reminder, a shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall, the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also recall that the color coding of the 8 position values is as follows. Positions 1, 4, 6, 7 are color coded black. Positions 2, 3, 5, 8 are color coded red. This will enable us to follow the effect of shuffles on Bessey sequences. In particular, it will allow us to detect whether the Bessey sequence structure has been preserved or whether it's been inverted. And once again, inversion means that the cards that originally began in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8, and vice versa. Also recall that the two Bessey sequences of order 8 are constructed in the following two ways. As a dichotomous sequence of order 8 in which the 1s are found in positions 1, 4, 6, 7, and the 0s are found in positions 2, 3, 5, 8. The inversion of this Bessey sequence is as follows, and what happens here is the 0s and 1s switch places in their roles relative to their locations within the sequence. So in particular, now the 1s are in positions 2, 3, 5, 8, and the 0s are in positions 1, 4, 6, 7. Our first shuffle for today is shuffle 41, top row on the left. I call it the R-LR. Now the R here stands for repeat, so it's a repeat LR shuffle. So let's go ahead and demonstrate this shuffle. So we'll begin with our ordered packet 1 through 8 so that we can follow the movement of these 8 cards. Okay, so how this works then is it is an LR shuffle. So you begin just in a normal fashion when performing an LR shuffle. So no difference there. Now what you do is you take each half and then perform an LR shuffle on that half. Okay, so we just go like this. There we go. Do the same thing with the second half. And in the case of a packet of 8 cards, it inevitably leads to 4 pairs of cards. And so the stacking for shuffle 41 will be as follows. 1 gets stacked on top of 2. 1 and 2, as a set, get stacked on top of pile 3. That set of 6 now gets set on top of pile 4. So you're simply stacking from left to right. That's all you're doing. So let's take a look at the new ordering of the cards. Okay, so we get 3, 7, 1, 5, 4, 8, 2, 6. So in Cauchy's 2-line notation, we obtain the following. Of course, the top row is always the same, 1 through 8. And then the bottom row is 3, 7, 1, 5, 4, 8, 2, 6. And we can convert this to cycle notation as follows. 1 goes to 3, so we have an arrow from 1 to 3. 3 returns back to 1, so it cycles around. So that completes a 2 cycle, which is also called a transposition. What happens to 2? 2 goes to 7, so we have an arrow from 2 to 7. 7 returns back to 2, so it cycles back around, so we get a second transposition. What about 4? 4 goes to 5, an arrow from 4 to 5, and then 5 returns back to 4, so we get a third transposition. And finally, 6 goes to 8, so we have an arrow from 6 to 8, and then 8 returns back to 6, so we get our fourth and final transposition. Color coding the digits, we obtain the following. And recall that digits 1, 4, 6, 7 are color-coded black. Positions 2, 3, 5, 8 are color-coded red. So we find that black 1 gets sent to red 3, which gets sent to black 1. Red 2 goes to black 7, which goes to red 2. Black 4 goes to red 5, which goes to black 4. Black 6 goes to red 8, which returns back to black 6. So here we see that each value gets sent to a value of the opposite color. And when that happens, we say that inversion has occurred. So let's go ahead and demonstrate that using our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. Okay, so this is where we're beginning. So according to what we just found, if we perform this shuffle, we should get an inversion of this sequence, namely 0, 1, 1, 0, 1, 0, 0, 1. So let's check that. So once again, the RLR begins just like an LR shuffle, left, right. And now you take each half and perform an LR shuffle on each half. And then the stacking for shuffle 41 is from left to right, as we just demonstrated. Okay, so we should get back 0, 1, 1, 0, 1, 0, 0, 1, which we do. And taking a look at the shuffle diagram, top row on the left, we can see that we should expect double arrows between the values 1 and 3, 2 and 7, 4 and 5, and 6 and 8, since we have 4 transpositions. And that's what we see. We have a double arrow between 1 and 3, 2 and 7, 4 and 5, and 6 and 8. And we can clearly see that inversion has occurred. So what originally began in positions 1, 4, 6, 7 moved to positions 2, 3, 5, 8, and vice versa. Also, since shuffle 41 is a product of transpositions, it has order 2, meaning if you perform this shuffle twice, it returns the packet to its original order.